Let's have a look at an example on the percentage analysis. Let us say we have two synchronous missions which are of two different ratings. Now let me consider that I have a synchronous generator which is 10 MVA rated and 11 kV generator, and its impedance, I say that it is percentage reactance is 10. Now let us also consider another generator which is 100 MVA but 25 kV with the percentage reactance as 10. This is my generator 1 and this is my generator 2. Now both the generators does have the same percentage reactance. Now if you want to look at the actual reactances of these two generators, are they same or not? Because I have two different machines of two different ratings. The fundamental understanding from the concept of percentage quantities tells us that if the percentage values are same, then they should have an actual value to be same. But the way we defined the percentage value in our analysis is slightly different. That makes the actual quantities of these two machines to be different. So how do we get that? We know that the percentage value of reactance is the actual value of reactance upon Z rated multiplied by 100. Now, if that is the case, you need to have the percentage value of reactance for the first mission here to be actual reactance of the first mission divided by rated reactance of the first mission multiplied by 100. Whereas the percentage reactance of the second mission here is the actual reactance of the second mission divided by Z rated reactance of the second mission multiplied by 100. And now, what is the rated reactance of this mission and what is the rated reactance of this mission? If you look at the rated reactance of the first mission, that is V rated reactance square divided by S rated. This is for the first mission. You know that the V rated is 11 kV square upon 10 MVA. This is actually 121 divided by 10, which you will say 12.1. And similarly, if you want to look at what is your Z rated 2, I'm not writing the expression, but you can say that this will be 25 kV square divided by 100 MVA. So this is 625 divided by 100, which is 6.25. So when you want to get the actual values of the reactances here, that X1 actual reactance is 10%, which is 10 multiplied by, because percentage reactance is 10 here, multiplied by Z rated 1, that is 12.1 divided by 100. Similarly, you have your x2 actual to be 10 percentage multiplied by 6.25 divided by 100. You can say that this will be 1.21 ohms, and then this will be 0.625 ohms. Now this clearly indicates that when two machines are of the different ratings, though the percentage reactance of both the machines are same, the actual reactances are not same. The basic reason for this to happen is that the percentage quantities that we have here, the percentage quantity here or percentage quantity here, are represented with refer to the ratings here. And the whole purpose of choosing the percentage analysis or some kind of analysis is to have a common reference for all of them, even when they have a different ratings. Now we have a different rating, but still we ended up in having a different reference in our quantities representation. So now the simple trick here to solve this problem is that, okay, fine, I have an actual value 1 here, actual value 2 here, maybe 3, 4, 5 and so on, but it's better to have the reference to be same. Not like generated 1, generated 2, generated 3 and so on. So now if you wanted to have the same reference throughout all the machines for the changing actual quantities, then that is what you call it as, yes, I have an actual value and I have a base value. So now the actual values keep changing, but the base should remain same. Even if the machines are different, they are of the different rating, then I'm supposed to have the same base value. That's where the concept of the per unit analysis comes into picture. And that's what is the basic problem with the percentage analysis, where your quantities are represented, referred to the ratings of the machines itself. Now, if you don't want to refer them to the ratings, and if you want to refer all the quantities of impedances to a common impedance reference, and if you want to refer all the quantities of currents to a common reference of current, if you want to represent all the voltages to a common reference of the voltages, that's what we call it as per unit quantities. So the whole reason why we ended up in getting a different actual values in spite of having the same percentage quantity is because we referred reactances with refer to the ratings of the machine. Now, the idea of the per unit analysis is to have defined a single base reference for all the reactance measurements or all the reactance quantities, or a single reference base value for all the currents, a single reference base value for all the voltages. So that's what we would like to have. So the fundamental expression that you expect for the percentage reactance is, it may be X actual, maybe 1 or 2 or 3 or whatever it is, but you will have your Z base, or you can say your Z reference, to be single. That's the whole idea. So now we can define our per unit value as its actual value of any quantity in any units divided by base value of the same quantity in same units. So what do we mean by that? Here we understand this is actual value by base value. Now what do you mean by actual value, base value? That is fine, of any quantity in the numerator, but you say that the same quantity here. What is the meaning of that? If you are getting the per unit value of impedance, then you should have your base value of the impedance. This is the actual value and this should be the base value. Now if you're having the current actual value, then you will have the base value also to be current here. If you have voltage actual value, then you will have voltage base quantity here. If you have power, that is S actual value, then you will have your S base here. That's what you mean by having the same quantity in the numerator and denominator. What do you mean by having the same units? Because if the quantity is same, then we expect the units also to be same. But why are we so specific about the units in defining the per unit value? The reason is, here you may have your current quantity to be same, but sometimes we end up in giving the current in the numerator to be in amps, current in the denominator to be in kiloamps, or voltage in the numerator to be volts and the voltage in the denominator to be kilovolts. You should never do that. This is what is going to be wrong for us. So you need to make sure that the units of the quantity, the actual quantity, and units of the base quantity are same. Though we have the units for the impedance, current, voltage, and power are predefined, but that suffix, that adjective that we have, the additional kilowatts, kiloamps, kilovolts, all this is where we make wrongly represent the units of the same quantities. That is why we are so specific about giving the units also to be same there. So the per unit value is actual value of any quantity in any units divided by base value of the same quantity in the same units. So now there is a difference that we get when you have transformers in the power system. We try to have the voltage bases to be different on both the sides of the transformer according to the turns ratio of the transformer. That brings a lot of advantages in the power system computations, which we'll be discussing further. But to start with, this is what is the per unit value for us. So the actual value by base value, but make sure that you have the same quantities and in the same units. It may be impedance, current, voltage, or power. And now, the another tricky thing that you need to remember at this definition itself is that we gave these four quantities, but we haven't talked about resistance or reactance. We haven't talked about real power or reactive power. The reason here why we haven't specified anything about the resistance or reactance is nothing but you have an impedance which is R plus jx. Means if you have a base for an impedance, then that is the same base you can use or you will be using for the resistance as well as the reactances. Similarly, you have a power P plus jq, which is nothing but the complex power S. So if you have your S reference, then the same reference will be used for real power or reactive power. That's what we've discussed while we were discussing the percentage analysis, that the real and imaginary part of a complex number will not have a different reference, and the reference will be exactly same as the complex number magnitude itself. So that means the magnitude of S and magnitude of Z will be the references for the resistance and reactance or real power or reactive power. So now we have the definition for the per unit value. Then we'll try to see how do we use this kind of representation to analyze the power system circuits.